Hello and welcome to lecture number 5 of the course Robot Motion Planning. In the last class we had looked at the rotation matrix and we saw the various properties of the rotation matrix, and we also solved a few problems, and then we moved on to the homogeneous transformation matrix that relates the coordinates of a frame which is rotated and also translated with reference to the reference frame, right? And then today we'll move on to the next part, that is how do you assign frames. And then after you assign frames, how do you find the relation between the end effector frame to the base coordinate frame? Okay, and then we'll look at forward kinematics, inverse kinematics, and also things like singularities. Okay, so today we continue with forward and inverse kinematics. But before we go to forward and inverse kinematics, I will very briefly revise what we had done in the rotation matrix and the homogeneous transformation matrix. So what we have seen in the last class is that the rotation matrix consists of a 3 by 3 matrix, and we say rotation about Rz, the z-axis, by an angle theta is the rotation matrix cos minus sine cos 0 0 1 0 0. We also looked at the various properties of this matrix, which means that the determinant of this matrix R is equal to 1 and it's a proper orthonormal matrix. Now, because it's a proper orthonormal matrix, the inverse of R inverse is equal to R transpose. Apart from this, it has the properties that the mod of the x column, y column, and the z are equal to 1, and the dot product of x dot y is equal to x dot z is equal to y dot z is equal to 1, is equal to 0, sorry. Okay. Now, because of this, we have noticed that although this matrix is 3 by 3, it has 9 elements, but it does not require 9 parameters to specify the rotation of a body in space. You only need 9 minus 6, that is equal to 3 parameters, which are also called the direction cosines. So the direction cosines, okay? And these 6 are basically the constraints which are coming from this. These are the 6 constraint equation. Okay, so this is just to revise about the rotation matrix. Then we moved on to the homogeneous transformation matrix, and we said that if you have a frame, this is my fixed frame, okay, let's call it frame A, and this is x, y, z. Now, if you have another frame which is rotated and translated with reference to this, so I have a frame which is rotated and translated. So this is my frame B, and this is my x dashed, y dashed, and z dashed. And suppose I have the coordinate of a point in frame B. So the coordinate of a frame of a point in frame B is here. Let's call this point P, and we're expressing the coordinate in frame B, which is equal to UVW. Okay, and now I want to find what is this UVW in terms of the frame A. So I want to find what is AP, which is my XYZ. Okay, this is something I want to find. Now, how do you find the homogeneous transformation matrix? So what we see is that I complete this vector diagram like this, and then I write my closed loop equation. This is APB ORG. The meaning of this is the ORG means the distance between the origins of 2 frames A and B. This is AP, and that's my BP, right? So I can write this as AP is equal to APB ORG plus R, the rotation matrix, into BP. So we need a rotation matrix there. Why? Because otherwise the frames B and A are not aligned. There is a rotation between them. Okay. Now I can write this mathematically in the form of a matrix as x, y, z. 1 is equal to the rotation part. So this is my rotation part. This is 0, 0, 0. This is 1. This is my dx, dy, dz, and this is my UVW. Okay. So this matrix, which is a 4 by 4 matrix, is called the homogeneous transformation matrix, and it has 4 parts. This is the rotation part. This is the translation part. Translation of what? Translation of origins. Okay, and this is called the scale parameter, and this is called the perspective. Okay, so this matrix relates the coordinates of a point which is expressed in a rotated and translated frame to that of the reference frame. Okay, Now, the next thing that we'll need to see is we'll need to move on to the assignment of frames. So far, we have said that this is an axis system or this is a frame and this is XYZ axis and just rotating and things like that. But then how do we assign this axis systematically in a robotic system? And that is something which we'll see now, and that is what is called axis assignment as per DH notations. DH stands for dinner with Hartenberg notations. Now, in this DH notations, basically we are going to systematically assign the axis. So let me look at, let me say that this is a robotic linkage. First of all, understand this is 3 DOF, degrees of freedom, which has 3 revolute joints. It is planar. What it means is that the axis of this mechanism is pointing out of the plane. Okay. So that's the first thing that we see. Now, as per DH notation, the first thing is we assign the z-axis as the axis of rotation or translation. Okay, so this is the first thing we see. So when you see a robotic mechanism or a linkage like this, the first thing that you do is to look at where is the axis. What kind of mechanism is it? Is it a revolute joint, translating joint, spherical joint? How many degrees of freedom? Is it planar? Now, once you understand this is these are the joints, then you assign the z-axis. So let me assign the z-axis out of plane. So my first one is z0, which is not moving, and z1 is the next axis. Okay, so it basically means that I'm assigning my axis 1 to the first link. So this is my second, z2, this is z3. Okay, so this is the origin which is assigned on to the link 3, link 2, and link 1. Okay, and z0 is the one that does not move. So the next thing that we need is to figure out where is the x-axis. Now the x-axis is the shortest distance between the z-axis. Okay. Now in this particular case, we can see that the z-axis are parallel, so you can very easily find out the shortest distance. Also, the first x0 we can put horizontally. Why? Just convention. We say that the x-axis is horizontal. Okay, that's the reason we put it there. The next one will go along the link, which is x1, then it is here x2, and that is my x3. Okay, so we have assigned our x-axis, y-axis, and z-axis, you can see as per DH notation. Okay. Now we do not normally assign a y-axis because the moment you fix x and z, y gets automatically fixed because of the right-hand rule, right? So we don't assign y-axis. We just assign the z-axis first, then we assign the x-axis. Okay, and these are my link lengths. Let's say L1, L2, which is already given, and that is L3. Okay, so this is how we assign axis as per DH notation. There is one exception. Now the exception is if the z-axis, then x is perpendicular to plane containing z's. Okay, so in this particular case, the z-axis are parallel to each other, they are not intersecting. But in case the z-axis are intersecting, then there is no shortest distance between them, right? So in that case, the x-axis is perpendicular to plane containing the z-axis. Okay, so let's have a look at this case. So let me draw another robotic mechanism where this happens. So if you can visualize, so there is a linkage like this, and there is a link here. Okay, that is a link, and this can rotate about this. So that's my base, and if you can imagine, then this is my axis. That is the first axis. So this can rotate like this. That's the second axis, which can go up and which can rotate like this. Okay, and there is the third axis which can rotate like this. Okay, so the axis 1, axis 2, axis 3. I hope you can imagine. So this is something similar to our shoulder, to our waist. So the waist axis is vertical, right? The shoulder axis is here, and this can be the elbow axis. Okay, similar to the human hand. So now let us assign our axis as per DH notation. So our DH notation, the first one says that the first one is along the axis of rotation or translation. Here there is a rotation axis. This is another rotation axis, right? And this is my third rotation axis. Okay, so we have fixed our 3 rotation axis. Let us call this Z0 fixed and 1. This is Z2 and this is my Z3. Okay, now what you see is that Z0 and Z1 are the same axis. Okay, but Z1 and Z2 are perpendicular to each other. That means they are intersecting now. So in that case, we find the plane of intersection. This is the plane of intersection. This is the plane where Z1 and Z2 lie. So the x2 will be perpendicular to this plane. So my x2 is here. So I can put my x0, x1 and x2 along that direction. And this is my x3. Okay. So this showed the rule of exception where the z axes are intersecting. Now I'm doing it very quickly as just whatever basics is required for us to go ahead in this course. So those of you who would like to study this part of DH parameter assignment for different kind of robotic mechanisms, okay, it can get tricky at times. So you can refer to the textbook Introduction by Robotics, Introduction to Robotics by John Craig. Okay, so this chapter, this textbook gives details. So any robotics textbook actually gives details on DH parameters. Okay. You can also refer to the NPTEL notes, NPTEL lecture on Intro to Robotics. Intro to Robotics. Okay, so there is an Introduction to Robotics course where this is done in much more detail. Here I'm just giving you the very basics, just enough that is required. Okay, so here we have seen that you assign your axis as per DH notation like this. And then after we have assigned our axis, we have to find what is the relation between the axis so that we can go from one frame to another frame. So let's look at that now. So this is our manipulator where we have three links like this, and this is my Z0, Z1, this is Z2, this is Z3, and this is my X0, X1, X2, and X3 frame assignments. So I assign my frames. Next, I want to find, so what is theta here now? Something I missed out maybe here is what is the link angle? The link angle theta is the angle between the x, between x-axis. Okay, so in this particular case, this is my theta 1, that's my theta 2, and that's my theta 3. So the only variable here is theta 1, theta 2, theta 3. This is the rotating joint system, right? So here also the angle is only between the x-axis, so the thetas are there. So theta 1 and theta 2 are there, and theta 3 is here. Okay. So in the so the theta is the joint angle. So in this case, what is the joint angle? So in this case, the joint angle, let me draw it in red. So this is my theta 1, there's a theta 2 there, and there's a theta 3 there. Okay. Let us go back quickly to the homogeneous transformation matrix. That is the one I'm going to use now. Okay. So the homogeneous transformation matrix consists of 4 parts as shown here. This is the rotation matrix, the rotation part. Rotation between what? Rotation between the 2 frames. This is the translation part, which is the distance between the origins of the 2 frames. This is always 0, 0, 0, this is always 1. Okay. So in this manipulator system, I'm going to write the transformation matrix between the frames. So how many frames are there? There are 3 frames here. So the first transformation matrix is T0 to 1, which is given by, so let me write it like this. Okay. So this is always 0, 0, 0, that's always 1. Now look at frame 0 and frame 1. The origins are the same, so there is no distance between them. So I put it straight 0, 0, 0. What is the rotation between them? It's a rotation about z axis. All the rotations are rotations about z. So you know what is rz. So C1 minus S1, S1, C1, 0, 0, 1, 0, 0. So cos theta 1 minus sin theta 1, sin theta 1, cos theta 1. Now if you can connect the dots, so what I just said some time back, that in the DH notation, the z-axis is the axis of rotation. So you'll always get rz theta. This axis will always be the same. Okay, that simplifies matters. So this is the first one that relates the first frame to the 0 frame. The second one is relating the first frame to the second frame. Now have a look at the first frame and the second frame. This is 0, 0, 0. This is 1. Where is second frame? It is here. So second frame is here. That's my second frame. The first frame is here. Okay. So what is the angle between the x-axis again? So this is the angle theta 2. Okay, that's my angle. So this is going to become, the rotation is again z, but the variable is theta 2. So this is going to be cos 2 minus sine 2 cos 2, 0, 0, 1, 0, 0. Now, what is the distance between the origins? The distance between the origins is L, right? So let's say this is L1 and that is L2. Okay. So what is the distance between the origins? The distance between the origins is this distance, and it is along the x-axis. Okay. So the distance between the origins is a distance of L or L1, and there is no distance in the y and the z direction. So this is how we write the homogeneous transformation matrix. The third one is, 2 to 3. Now what is this matrix? This matrix is again 0, 0, 0 and 1. Now what is the rotation? Rotation is corresponding to theta 3, and it's a rotation about z-axis, right? So the rotation is here. So it will become cos 3 minus sine 3 cos 3, 0, 0, 1, 0, 0. Now what is the distance between the origins between frame 2 and frame 3? So it is this distance, the origins of frame 2 and frame 3 along x2 now. Okay, and that is my L2. That is 0, 0. Okay. So now I have found the relationship between the third frame to the second frame, second to first, and first to 0. So if I want the relationship between the 0 frame and the third frame, all I need to do is to multiply all of this 3 matrices together, and I will get, so I'm going to multiply T0 to 1 cross T1 to 2 cross T2 to 3, right? So this is what we call frame assignment by DH parameters, and then multiplying it to get the relationship between the third frame to the first to the 0th frame. Now when the manipulator is moving in space, because the 0 frame is not moving, it's only the third frame which is moving. The other frames can move, 0 frame is not moving. So we can find the relation between all the frames and the 0 frame now. Okay, in fact we can find the relation between any frame and the 0 frame. Okay, so that is why we put the 0 frame as the reference frame which is not moving. Okay, so everything is found with reference to that 0 frame now. And how can we find it? Simply by multiplying it like this. So suppose theta 3 changes, just for example, just for explaining. If theta 3 changes, what will happen is this end effector will come here. Okay, and that will be taken care of by this matrix. Okay, so the rotation takes place here, right? So if theta 2 changes, then the rotation will take place in the corresponding this matrix. Okay, so you can see that each of this has a variable which is theta 1, theta 2, and theta 3. Okay. So when I multiply them out, this is what I get. So next thing we need to do is to multiply this out. So let's multiply it out. So when we multiply all of them, I multiply T0 to 2 first, which is equal to T0 to 1 into T1 to 2, and this comes out to be. So let us multiply this out. Please multiply it. You can multiply it out like this. Okay. So you can see when you multiply this versus into that, what will we get? Cos theta 1 cos theta 2 minus sin theta 1 sin theta 2. That's the first term. You know how to multiply matrices, right? So if you multiply them out, what you'll get is cos 1 2 minus sin 1 2 sin 1 2 cos 1 2 0 0 1 0 0. This is L1 cos 1 and this is L1 sin 1, that is 0 0 0 0 1. Okay, you can verify this. So cos 1 2 means cos theta 1 plus theta 2. Okay, so similarly sin 1 2 means sin theta 1 plus sin theta 2. Okay, I'm writing it in short. Then we continue, multiply this 0 to 3, so it becomes T1 0 to 2 into T2 to 3. So you take this matrix and multiply it into T2 to 3. Okay, what is 2 to 3? 2 to 3 is this matrix. Okay, now multiply it similarly, and what you'll get is you can multiply and see by yourself. Cos 1 2 3. So cos 1 2 3 means cos theta 1 plus theta 2 plus theta 3. Okay, minus sin 1 2 3 0 0 1. This is now sin 1 2 3 cos 1 2 3. This is 0 0 1. This is L1 cos 1 plus L2 cos 1 2, and this is L1 sin 1 plus L2 sin 1 2. This is 0, that is 0 0 0 1. Okay, now in this matrix that we have got, multiplied out, see if it makes sense. That's very important here. Okay, so this has 4 parts, as we said. This is the rotation matrix. Now the rotation set cos minus sin sin cos, which is a rotation about z axis, and this is theta 1 plus theta 2 plus theta 3. So the total rotation that this manipulator has had is the sum of theta 1 plus theta 2 plus theta 3, which you can see from here, right? So the total end effector rotation, this is the third frame. So the total rotation of that third frame will be the sum of theta 1 plus theta 2 plus theta 3, and that's what we're getting here. And this is the rotation about z. Okay, so it's correct. Okay. Now what about this? This is del x, motion in the x direction, this del y, and this del z. So this is how much the origins have moved in the x direction. This is how much the origins have moved in the y direction. Okay, and this we can see from here. Let's go back there again. So if you see from here, how much the origins have moved can be found from here. So in the x direction it is this much, y direction is that, and z direction is, sorry, x, y, there are 3. So it is going to be L1 cos theta 1 is this distance. Then the next distance is L2 cos theta 1 plus theta 2, right? So where has this fellow moved? If I say that is my xy, okay, then in the x direction it has moved by L1 cos theta 1 and then L2 cos theta 1 plus theta 2, which we are getting here. In the y direction it has moved by how much? In the y direction it has moved by, this much, that is L1 sine theta 1 plus this much, which is L2 sine theta 1 plus theta 2. So that is what we are getting in the y direction. Okay, so what you are seeing here is that this is the motion in the y direction, that is in the x direction. So this point here, which is the origin of the third frame, has moved in the x direction and y direction by that much amount, okay, plus the angle that the third axis is making, x3 is making with respect to x0 is sum of theta 1 plus theta 2 plus theta 3. So what we have obtained here is correct. Okay, so it is very important for you to be able to correlate. Okay, it's extremely important in robotics to be able to correlate the mathematics that we are doing plus the real system. If you cannot correlate, then there is no point. Okay, so we see that from here we get the coordinate of that point, x and y coordinates of that point, plus the rotation of the plus the orientation of the. So this gives me the position of the third frame, and this gives me the orientation. Okay. So now you understand how do we assign axis and how do we find the combined position orientation of the third frame or the last frame with reference to the 0 frame. Okay. Now let's proceed further and look at forward kinematics and inverse kinematics. So what is that we need to do here is, let's look at this example. Okay. So suppose I'm giving you this point xy. There is a corresponding theta 1, theta 2 and theta 3. Okay. We are going to assign axis z0, z1, z2 that I have just explained, z3. Okay, this is my x1, this is x0, and that's my x2 and x3. Okay, now what are the variables here? So when a robot moves, what changes? The thetas change. The other things are fixed, right? Link lengths are fixed. Okay, so we have two requirements in the forward direction and the reverse direction. That is, given theta 1, theta 2, theta 3, okay, find xy and phi. Phi is the total rotation of the third axis. Okay, so this is one, and this is basically what we say is the forward kinematics. Okay, so input to this can be theta 1, theta 2, theta 3, and the output of this is going to be the position xy and phi of the end effector. So this is what we call by forward kinematics. Now inverse kinematics, the input is this one. So this is inverse kinematics, okay, in which case the input is the x and phi, so xy and phi, and the output is the thetas. Okay, say for example, let us look at this in let's take a numerical example which we understand better. In this the same manipulator, this is the point xy. Okay, it is actually x3 and y3, so L1, L2, theta 1, theta 2. This is my x0. You can imagine this here y0, z0 is this side. Okay, so what is xy? Geometrically, x is equal to L1 cos theta 1 plus L2 cos theta 1 plus theta 2, geometrically, right? What is y? Y is equal to L1 sine 1 plus L2 sine 1, 2, right? So now suppose in forward kinematics, I give you L1 is equal to L2 is equal to 1. unit, and theta 1 is equal to theta 2 is equal to 30 degrees. Okay, so now you can find xy. Okay, find xy using forward kinematics. So I'm giving you theta 1, theta 2 is 30 degrees, and L1, L2 is 1. Find what is the xy for this corresponding position. How would you do that? Simply take the values of theta and put into this equation. Right? Now, in inverse kinematics, I'm going to give you the xy position. Suppose I say x is equal to 1.5 and y is equal to 1.0. Okay, find theta 1, theta 2, theta 2, and theta 3. So, and phi is equal to something. I give it to you. Okay. Now you find theta 1, theta 2, and theta 3. This is the inverse kinematics problem. So this is the statement of the inverse kinematics problem. Okay, so I say phi is equal to 0.5, just for example. Okay. So now I hope you understand. How would you do that? You take xy now. You take the values of x and y. I said it is 1.5 and 1. And then try and solve for theta 1, theta 2. Okay. So this is the meaning of forward kinematics and inverse kinematics. Now obviously you understand that forward kinematics is much more simpler, because given the values of theta 1, theta 2, theta 3, link lengths are of course given. You just put them in this equation A and then you solve it. But inverse kinematics is the one which is more tricky, because you can see that although there are two equations, two unknowns, this appears in the form of sine and cos. And sine and cos solving like this is not very easy. Sometimes you may be able to solve, sometimes you may not be able to solve. And there could be multiple solutions. Because you know that sine and cos always have two values for every values. For example, for sine 90 is equal to sine 270 is equal to 1. Okay, so you're getting two values for theta here. Similarly, for cos also you'll be getting two values of theta. Okay, and that is what makes the solution difficult. This is only two, but suppose you have a large manipulator like 6 degrees of freedom or 10 degrees, then there are 10 thetas now, and they will all come in these combinations. So it's extremely difficult to solve. Okay, so we are not going into details here. Again, if you're interested or in robotics in this particular aspects of kinematics and forward inverse, please look at the textbook I just mentioned or refer to the notes, refer to the class on NPTEL on Introduction to Robotics. Okay, here let us proceed and just find out the relation. So this is basically forward kinematics and inverse kinematics. Now let us see how do we do the inverse kinematics of this two-link manipulator system which is required for us. Okay, very simple example again. Let us look at this two-link. I'll further simplify this. So this is my two-link manipulator system. Okay, so this is my theta 1, theta 2, theta 3. Okay, and my final matrix has come in the form, you remember what the final matrix was. Okay, so in the final matrix what we got was from here. So this is what we got, x is equal to that and y is equal to that. Okay, so I can solve theta 1, theta, so I can solve theta 1, theta 2 from here and then theta 3 from here. Okay, so what I do is I first write down x and y and try and solve for theta 1 and theta 2. So I'm going to write down x and y. Let me drop this off. So x is equal to L1 cos theta 1 plus L2 cos theta 1 plus theta 2, and y is equal to L1 sin theta 1 plus L2 sin theta 1 plus theta 2. Okay, now what you see is that there is equation 1 and equation 2. Equation 1, equation 2. Two equations, two unknowns, but the way it appears here, you cannot solve so easily. So there is a cos and a sine. So what we do is we square and add 1 and 2. So squaring and adding equations 1 and 2, what we get is x squared plus y squared is equal to L1 squared cos 1 squared plus L2 squared cos 1 2 squared plus twice L1 L2 cos 1 2 plus L1 sin 1 squared plus L2 squared sin 1 2 squared plus twice L1 L2 sin 1 2, and then we add. Now what you see here is that there is cos 1 squared and sin 1 squared. Okay, and then there is a cos 1 2 squared and sin 1 2 squared, and then there is twice L1 L2 twice L1 L2. So squaring and adding like this, what we get is this x squared plus y squared is equal to L1 squared plus L2 squared. So cos 1 squared plus sin 1 squared is 1, so I'm not writing it. Okay, plus twice L1 L2 cos 1 2 plus sin 1 2. Okay, now if I further simplify, x squared plus y squared is equal to L1 squared plus L2 squared plus twice L1 L2 cos 2, because this one will come out of the form cos theta 1 plus theta 2 minus theta 1. So this and this will cancel. So this and this will cancel. So you'll be left only with theta 2. Now something important here is when I look for when I see this further, I can get cos 2 is equal to x squared plus y squared minus L1 squared minus L2 squared, okay, divided by twice L1 L2. Okay, now we should not take a cos inverse here. Okay, so this is something which you need to understand carefully, that we should not take a cos inverse to get cos 2. Why? Because cos 2 has two values. What are the two values? For any xy here, this is xy, this is theta 1, this theta 2. Okay, that this is one value of theta 1, theta 2. What is the other value? So for the same xy, you can have another configuration which is like this, and the value is the same actually. I hope you can understand this. Okay, this is my x, that's my y. Okay, so for this value of theta 1, theta 2, you get xy. But if you have the other value, this is my theta 1 dashed, and that is a minus theta 2. So you get theta 1 dashed and a minus theta 2. You get the same xy. And why is this happening? This is happening because the sine and cos have two terms. Okay, so this shows you that there are two solutions actually, and what we call multiple solutions. Okay, so if you have higher degrees of freedom, you will have more number of solutions. Okay, so because of this, we do not take the inverse there, because you will get a plus and a minus, you will get this. Now the software, if you're writing a computer program, it will not be able to distinguish between minus and plus. Okay, so this part is the one that causes the problem, because cos of minus theta 2 is equal to cos of theta 2. So as far as the computer is considered, it cannot distinguish. But as far as the real system, they're all different. You can see theta 2, minus theta 2 is up there, and theta 2 is here. So they're completely different angles. Okay, so what we do is we don't take a minus there, but we take this function, we convert it to sine 2. So sine 2 is equal to root over 1 minus cos 2 squared. Okay, and then we take theta 2 as an a tan 2. A tan 2, it's a special function, we take S2 and C2. Okay, so we use the special function called a tan 2, and this function basically takes the positive sine 2 and the positive cos 2. Okay, and then it finds one solution. So once you have found this solution, so one solution is this. What is the other solution? So other solution is minus theta 2. Okay, as we have seen from here, if this is your plus solution, if this is your plus solution, that's the minus solution. Okay, so that is the minus solution. Okay, next we need to find what is theta 1. So for theta 1, again what we do is we use a geometrical method. You can use algebraic methods also, but for simplicity we are using geometrical method here. So we have our linkage like this. It's very simple. Okay, so let's say this is my point xy. Okay, this is my x-axis, that's my y-axis. Okay, so this is theta 2, this is theta 1. Now let me do this construction quickly. So this construction I do, this is a triangle here and there is another triangle there. So this is one triangle here and there is another triangle there. Okay, so what I do is I define two new angles. One angle is here, I call this angle alpha, and I call the other angle, and I call this angle beta, this angle as beta. Okay, now from geometry we can see that theta 1 is equal to alpha minus beta. So if I can find alpha and beta, then I can easily find what is theta 1. Theta 2 is already known, we just found, and that xy coordinates are given. Okay, so now what we are saying is that in this equation that we just saw, so here in the inverse kinematics solution xy given, find theta 1, theta 2, right? Here if you see from geometry again, what we are saying is that what is tan theta 1? tan alpha. Tan alpha is this big triangle. Tan alpha is this big triangle. So tan alpha is y by x in that big triangle. So it has to go down straight like that, right? Okay. So that's my tan alpha. This is y and that is x, right? Now what is tan? So that is tan alpha. What is tan beta? Tan beta is this triangle, green and blue triangle. So tan beta is this triangle where it is equal to, and this is my length L1, L2, sorry. The lengths are there, L1 and L2. So what is this equal to? The opposite is L2 divided by the base, which is L1 plus L2 cos 2. So it is this triangle. Let me draw it in some other color. This triangle. Okay. So I hope you understand this. This part is equal to L2 cos 2. Okay, and this part is equal to L2 sin 2. And this is my L1. This is L1. Okay. Now we have seen, we have got alpha and we have got beta. Okay, now there is a formula tan alpha minus beta. Tan alpha minus beta is equal to tan alpha minus tan beta divided by 1 plus tan alpha tan beta. Now from here and here we can put the values in there. We have got these values, right? So now we can say that tan theta 1 is equal to tan of alpha minus beta, which we have found here. Okay, so this is something we are finding here. Okay, this is this one. So I can take then tan inverse. Okay, I can take a tan of this and I can find theta 1. Theta 1 is equal to a tan of this. Okay, so now we have been able to find theta 2, where we just found theta 2, and I'm also able to find theta 1. Okay, so this is basically showing the inverse kinematics of 2-degree of freedom system. If you are interested in the higher degrees of freedom system, please refer to the textbook. For us, this is enough for our motion planning, because motion planning of higher than this degree of freedom system becomes very, very complex. That is something you'll be seeing. Okay. Okay. So let's proceed now to the next topic, which is singularities and energy consumption when the robot is moving. Okay. So let's look at this robot here. X-axis, y-axis. Okay. Now this is my theta 1 and this is my theta 2. Now how does this robot actually move? There is going to be a motor at the joint. So there will be some motors attached to the joints, right? The motor will rotate and then the joint will rotate and then the end effector will rotate. So XY. Okay. So basically we want to find the relation between the end effector velocity and joint velocity. Okay. Why? Because we are interested in moving the end effector in space. For example, there is an obstacle here. I'm just giving an example. And you want to move the manipulator such that it goes like this. It doesn't hit the obstacle. Okay. In that case, you need to find the velocity, not only the position, the path, but you need to find the velocities that will take the end effector along this path, avoiding that obstacle. So you need to find the relation between the joint velocity, the end effector velocity, and the joint velocity. Right? Now, how do we get the end effector velocity and joint velocities? So what we do is we write the position relationship. We know that xy is a function of theta 1, theta 2 in this case. Okay. So, and the relation also we know L1 cos theta 1 plus L2 cos theta 1 plus theta 2, and y is equal to L1 sin theta 1 plus L2 sin theta 1 plus theta 2. Okay. Now we see that there are two variables, theta 1 and theta 2. And on this side we have x and y. So if I take the derivative, if I take the partial derivative of the first equation and the second equation, first with respect to theta 1, then with respect to theta 2. Okay. So what I'm doing is I'm differentiating equation 1 with respect to theta 1 and then with respect to theta 2. And then the second equation with respect to theta 1, then with respect to theta 2. So this I'm getting dx is equal to minus L1 cos 1 minus L2 cos 1, 2. And here I'm writing it in matrix form. So L2 cos 1, 2. The second one is dy. I'm differentiating again with respect to theta 1 cos 1 plus L2 cos 1, 2. and the second one is L2 cos 1, 2. In matrix form, I'm writing it like this. And here it is d theta 1, d theta 2. I hope you understand the way I've written it. Okay. Now this is, you can write dx by dt also. Okay, this also by dx by dt. That's fine. Okay. So first we are differentiating with respect to theta 1, then with respect to theta 2. So this is with respect to theta 1. This is with respect to theta 2. Okay. Okay. So now in short, I can write this as x dot is equal to j into theta dot. Now this is called the Jacobian that relates the joint velocities and the end effector velocity. So this is my joint velocity. Right, that's my joint velocity, and this is my end effector velocity, right? So the Jacobian relates, in this case it's a 2 by 2 matrix, and this relates the joint velocity with the end effector velocity. That means when I'm trying to follow a path or I'm trying to go to a point, this is going to determine what the relationship is between the joint velocities and the end effector velocities. And this is very important because, for example, to avoid this obstacle, you could do all kinds of things. You could go like this. Okay, you could go right from here and go like this and like this. So which path are you going to take? Well, you might say you'll take the shortest path. Okay, but shortest path need not be the optimal energy path. Okay, what we normally try to do is we try to minimize energy. So for that, this relationship comes into effect. Let's look at this relationship in a little bit more detail because it's very interesting and very important. So x dot is equal to j into theta dot. Okay. From the controller point of view, the controller would control theta dot of motors. Okay, that is the one it controls. So for a given end effector velocity, the controller has to control the motor velocities. Okay. So what is more important is theta dot is equal to j inverse of x dot. Okay. So for example, I have a manipulator here, and there is an obstacle here. As we are doing motion planning, this is a problem in motion planning. I want to go from this point to this point. Okay, this is my initial point I, and this is my goal point G. Okay, I want to go from there to there. Now there can be infinite paths. There could be no paths. Okay, so now if I want to find, suppose I find a path like this, like this, like this. I'm finding the path at the end effector level. Okay, not at the joint. Okay, now so for every point here, to take the end effector there, the motor controller must be able to give a particular joint velocity. So for this, I will be able to get corresponding angles, which is theta 1, theta 2. How many thetas are there? Maybe theta 4s are there. So for every point here, it has to do inverse kinematics and find what is the corresponding joint. Then the difference between this and this is an incremental velocity. Yeah, this is something I forgot to mention here, that this is an incremental velocity. Okay, so these are incremental velocities and these are not average velocities. Okay, like 2 meters per second. This is an incremental velocity. Okay, so this also, as we saw here, the difference between these 2 points is an incremental velocity. Okay, so if you want to follow a path, we must do inverse kinematics at every point on that path and then correspondingly go back to the joint velocities. That is one way of controlling it, right? If you want to control the end effectors. So what is very important for the controller is to be able to control the joint velocities now. And the joint velocity is given as theta dot is equal to j inverse. So this is equal to adjoint of j divided by determinant of j. This you know, into x dot. Okay. Now, in terms of energy, you see that the relationship is governed by the determinant of j. Determinant of j comes in the denominator. So if determinant of j were to go to 0, then theta dot will go to infinity. Now this basically means that infinite joint velocity means infinite energy, right? So to produce infinite velocity, you need infinite energy in the motor. Now that's not possible, right? And such points where determinant of j is equal to 0, these points are called singular points. Okay, singular points or singularities. So a robotic mechanism cannot go into a singularity. It cannot go anywhere near a singularity because the energy will suddenly become very high. Okay, Say for example, just for example, if this was the path and we found that there was a singularity here, then it cannot go anywhere near that. It must go off in some other direction. The question of singularity is very, very important here. The second is, this also gives us an indicator of energy. Okay, because you know that velocity and energy are related. Right? Because if you want more velocity, you have to give more energy. So there is a relation there between the motor velocity and the energy. Okay. So if you want to minimize energy, then you must maximize determinant of J. This is very clear from here, okay, from the previous relationship. So in this relationship, if you want to minimize the joint velocities, then you must maximize J to minimize the joint velocities. And the reverse also, if you want to maximize joint velocity, you have to minimize J. Okay? So to get minimum joint velocity, you have to maximize J. And to get maximum joint velocities, you must minimize J. So to minimize energy, you must maximize determinant of J. Right? So let us look at these two examples, singularity and maximum manipulation ability, or what we say the best way of doing a task. So let's look at this two-link manipulator. Okay, there's a two-link manipulator here, and I've assigned my x. This is my x, that's my y. So this is my theta 1, this is L1, this is theta 2, this is L2. Okay, the end effector point is xy. Okay, that's the point. Now I want to find what are the singular positions for this. What are the singular points? Now the singular points would mean that determinant of J is equal to 0. Okay, so let's find the determinant of J. Where is the determinant gone? This is the determinant. So if you multiply it out, what you'll ultimately get is determinant of J is equal to L1 L2 sine 2 is equal to 0. It's interesting that theta 1 is not in the picture at all. Okay, because of the sine and cos, what will happen is theta 1 will cancel. Please find the determinant and actually find. Now L1 L2 sine 2 is equal to 0. Now L1 L2 cannot be 0. L1 L2 cannot be 0. Right? Because they are linked lengths. So the only option is theta 2 is equal to 0. Now if theta 2 is equal to 0, then sine theta 2 is equal to 0, then theta 2 is equal to your 0 and 180 degrees. That's the only two possibilities. Okay, that means when it is theta 2 is here, so when it is fully stretched like that, okay, then theta 2 is equal to 0. Okay, and that's a singular position. Theta 1 is not in the picture, so it basically means that it will be a curve like this. Okay, so this is called the outside singularity, the boundary singularity. This is called the boundary singularity. And in case that is corresponding to theta 2 equal to 0. Now if it is fully folded like this, that's the other end. So that is also a singularity where it is 180 degrees, right? So if the link lengths are not equal, then inside also you'll get a region like that. Okay, so outside region and inside region. And this is my boundary singularity, this is the inside singularities. Now the 2 degree of freedom manipulator does not have inside workspace singularities. Okay, it does not have. Other manipulators can have 6 degree of freedom, 7 degree of freedom, they can have inside the workspace. But this 2 degree of freedom does not have. So we have seen where are the singular positions for this two-link manipulator, having 2 degrees of freedom, planar, 2 revolute joints. And we have answered that where are the singular points. Okay. Now, what about the next part? That is, this is a very important question, especially because we are doing motion planning. We have a link like this. Okay, 2 degree of freedom, 2 DOF. Okay, it has a work volume, you know the work volume is something like this. Now you can perform the task anywhere, right? Suppose you want to assemble 2 parts like this, assemble 1 part like this, inside another part like that. You can perform the task anywhere in the workspace. Okay, so for example, you can perform the task here. You can perform the task. So we are going to perform the task in such a way that the energy is going to get minimized. Okay. This is one example I've given. Now there can be other examples. For example, this is an obstacle. This is another obstacle. And there is a third obstacle here. We are doing motion planning. This is very relevant for us. Now suppose I want to take an object from here. Okay, I want to take this object from here, take it and insert it there. Okay, now how many paths can there be? There can be no path, there can be many paths. Okay, can you go this way? Probably no. Okay, can you go this way? Probably no. But going this way, you can have many paths. Okay, so if you have many paths in going like this, then which path will you take? You will take the minimum energy path. Okay, so minimum energy path. So if you take a minimum energy path, how do you find the minimum energy path? That is essentially by finding the determinant of the Jacobian again. Okay, or I want to do a task. Where would I do the task? I'll do the task in a place where the Jacobian is maximized. So this should be max. Okay, so if you want to maximize the Jacobian, we have seen L1, L2, sine 2 is the Jacobian. Okay, and if you want to maximize this, then theta 2 is equal to 90 degrees and 270 degrees. Okay, now so now we know where theta 2 is maximized. Okay, where your energy requirement will become minimum. So you should do the task such that this theta 2, where is theta 2? Theta 2 is here. Okay, this is 270, right? That is 270. So somewhere in that region. So the closer the arm, this is 90, the closer this is to 90 degrees, the more your energy is going to get minimized. So you should try and perform the task such, keeping that angle close to 90. Okay. Now it's very interesting that if you look at human beings, even for us, so we are looking at a human being, maybe next time you do this, please note. Okay. So when you're doing a task, for example, you're writing. Okay, you're writing. Okay, sitting and writing. Okay, let's say you're sitting on the chair and then writing. Okay, you're writing on that. Now, our arm is something like a two-link mechanism. This is one linkage, this is another linkage. So it's almost like two links, just the two links I have drawn. So in this two-link system, we are going to write such that, it's not correctly drawn. So in this two-linkage system also, we are going to do a task such that our energy is minimized. Okay, and we all do it like this. So when we are writing, you have multiple solutions. You can write in different ways. You can write in different parts of the workspace. Okay. Similarly, when you're doing a task, you are doing it at different parts of the workspace. Say, if you can imagine, the robot can do the task here, the robot can do the task here, 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 here. Where should the robot do the task? This is saying that it should do the task such that this angle is 90 degrees, and that region is somewhere here. Okay, so this is the optimal region. Now, in terms of writing, for example, a very interesting example, you see that our hands are having 2 degrees of freedom, and it is like this. You can approximate it. So in that case, your minimum energy would be in a case where your angle, this angle is 90 degrees. So next time you write or you do some task, you please note that the angle at your elbow is around 90. And in fact, we all do the task like that. Why? Because that is the minimum energy condition. Okay, so it is not only that we are studying robotics and we are talking of mechanisms and things like that, but this is valid even for us, because in our legs, hands, arms, body, we are also linkages, right? So whatever we are studying is valid for us also. So minimum energy, we have seen, you can ensure minimum energy by maximizing determinant of J. That's very, very interesting and very important for us, because we are always interested in finding paths where your energy gets minimized. Okay, so now today we have looked at homogeneous transformation matrix. Then we looked at how do you assign frames, and how do you go from one frame to another frame, and how do you find the relationship between one axis, the end effector axis, to the 0th axis or the base frame, such that when any of the joints move, we always find its relation with respect to the base frame, which is not moving. Okay. We also looked at singularities, and we also looked at this concept of energy minimization. So this is for a linkage system. Now let's move on to a mobile robot. Okay, let's say a mobile robot. In the case of mobile robot, what is the relationship? So mobile robot. So in this course, we'll be dealing with mobile robots, and also we'll be dealing with serial arms. So this is a mobile robot, differential drive mobile robot, which means that there are 2 wheels, which has omega 1 velocity, and this fellow has another velocity omega 2, and there's a caster wheel there which basically supports differential drive with caster wheel. So there's a caster wheel there. Okay. So there are motors connected here. There's one motor here and there's a motor here. So if the omega 1 is equal to omega 2, it will go straight. If omega 1 is greater than omega 2, it will turn on the right side. And if omega 2 is greater than omega 1, then it will turn on the left side. Sorry, if omega 2 is greater, yeah, this will be right turn. So omega 1 is greater, omega 2 is greater, it is left turn. That's how it moves. Okay. Now, the first thing we need to do here is to assign frames. So let us write our global frame. In the case of mobile robot, we assign a global frame which is not moving. Let's call this the I frame. Okay, this is my x-axis, y-axis, okay, which is not moving. I can call it x0, y0 also, the frame which is not moving. Then I assign a frame onto the robot. Okay, so what I do is I connect these two with a straight line, and the center point there, I call it point P, and then I take this in the forward direction as my x-axis. Okay, and this one as my y-axis. Okay, so I hope you understood. P point is the center point between the two wheels. And now what we are doing is, this is making an angle theta with x0, that's my x0. So now you can see that there is omega 1, omega 2 and theta is there. Okay. So now what is the relationship between the frames? Okay, or what is the relationship between the coordinates? We have a coordinate x, y here. So we have x, y and phi, x, y and theta. Okay. So to specify the position of the robot, we specify x, y of that point P. Okay, and theta is the angle the x-axis of the robot is making with the fixed frame. Okay. Now, what is the rotation matrix? Now z is pointing out of the plane. Okay, so it's a rotation about z again. Okay, so what is zeta? Let's call this zeta I is equal to rotation matrix r z theta into zeta r. Now you know that zeta I is equal to, what is the rotation matrix? Cos theta minus sin theta cos theta, 0, 0, 1, 0, 0, and this is your omega r. Okay, so when this robot is moving and is rotating basically, then we exactly know what is the relationship between the rotated system and the reference system. Now if I take the derivative of this, then if I take the inverse of this, if I want to find omega r, this is equal to r transpose. So it is cos theta minus sin theta. This is sin theta cos theta. Okay, this is 0, 0, 1. Is it okay? And this is omega I. Okay. So if I want to find the velocity, I just take the derivative of this and that. So I'm getting the joint velocity. So the velocity of the robot is also governed by this relationship only. Okay. So now we have seen that when mobile robot is moving, we are defining its position by this position x and y, and it is making an angle theta with the x0 frame. Okay, and the relationship is also governed by this rotation matrix, which is rz theta, which we have just studied. This is for a mobile robot also. Okay, this is my position xy. Okay. Okay. So today we looked at homogeneous transformation matrices. Then we looked at how to find forward kinematics, inverse kinematics, and then further we went on to look at the question of singularities, and I explained the importance of looking at energy, minimizing energy in terms of performing a task, finding a path in robot motion planning. So in the next class, we'll move on to the algorithms. From next class, we'll move on to the various algorithms in motion planning. And we'll start off with the bug algorithm, and then we'll move on to other kinds of algorithms which are there for serial arms, mobile robots. We also will look at topology, which is required basically because path planning is not done in Cartesian space. It is done in configuration space. So all these terms we'll be seeing as we go along. Okay, so we stop today. Thank you.